While playing tennis, Matt is 12 meters from the net, which is 0.9 or 9 tenths meters high. He needs to hit the ball so that it just clears the net and lands 6 meters beyond the base of the net. At what height should Matt hit the tennis ball? So this problem involves two different heights, the height at which he should hit the ball and the height of the net. And it also involves two different distances. It says that he's 12 meters from the net and that we want the ball to land 6 meters from the net on the other side. Because it has so many different measurements, I'm not even going to attempt to do this without drawing a diagram. Now, when you draw a diagram, it doesn't have to be like the most beautiful diagram in the world. I'm not even going to get a ruler or anything. It doesn't have to look spectacular. It just has to keep the distances sort of like vaguely in proportion. You don't want to do like a wildly inaccurate diagram, although it doesn't need to be super accurate. And you also want to make sure that you just get the distances labeled correctly. Okay, so I need to have, there's going to be Matt, the guy serving, there's going to be the net, and then there's going to be where the ball lands, right? So I've got the net right here in the middle. I've got Matt, my guy standing right here, who's serving the ball. And what's going to happen is he's going to serve the ball. Let me change colors here. He's going to serve the ball from a certain height. The ball is just going to clear the net and it's going to land over here somewhere. So he serves the ball from a certain height. It's going to just clear the net and it's going to land over there. So you can see that either my net's too tall or my guy's too short because he's serving the ball from way up here. The net's the same height as he is. Doesn't matter. Doesn't matter. So let's go ahead and put some of our measurements on. So the first thing it tells me is that Matt is 12 meters from the net. So that means this distance right here is 12 meters. And then the next thing in the problem, it says the net itself is 0.9 meters high. We hit the ball so that it just clears the net and it lands. Here's the next thing. It lands 6 meters beyond the base of the net. So the ball's going to land 6 meters over here. And then the thing that we want to know is how high, I'm going to need a different color here. How high, at what height should he hit the tennis ball? That's the thing that I don't know. Okay, so we've got two different triangles here. I don't know if you can see the two different triangles. I'm gonna highlight the triangles and then I'm gonna immediately erase the highlighting so this doesn't become too jumbled. But here's triangle number one, right there. There's my first triangle, and then my second triangle is right here. Second triangle is the really gigantic triangle. And believe it or not, these triangles are similar. And the reason that I know these triangles are similar is because they have two congruent angles. One of the angles they have that's congruent is that both of these triangles have a 90-degree angle. This is a 90-degree angle right here, and this is a 90-degree angle right here. So they both have a 90-degree angle because it's going straight up and down. And the second congruent angle that they have is this one, because both of the triangles share that angle. You notice when I highlighted the triangles, both of the triangles were highlighted on that angle. So these two triangles are similar because they have two congruent angles. And so the angle-angle similarity postulate, let me erase all this stuff first before I start writing. That's too much writing. The angle-angle similarity postulate says that these two triangles are congruent. Not congruent. We have two similar triangles because there are two congruent angles. Two similar triangles because we've got those two pairs of congruent angles. So if the triangles are similar, that means that their sides, the sides of these triangles, are in proportion. So what that means is, if I were to do a ratio of the sides of the smaller triangle, so the smaller triangle was this one right here. This was the smaller triangle. The sides of the smaller triangle, the height over the base of this triangle is 0.9 over 6. So I'm going to do a ratio of the height of the smaller triangle. Whoops, let's use more colors here. The height of the smaller triangle over the base of the smaller triangle. Because these triangles are similar, their side lengths should be proportional, which means if I do a ratio for the larger triangle is like the entire shape. If I do a ratio for that larger triangle, that ratio should be equal or proportional to the ratio that I just wrote for the smaller triangle. So let's do a ratio for the larger triangle. So the ratio for the larger triangle is going to be the height of the larger triangle, which was x, over the base of the larger triangle. And this is really the tricky part here. You might be tempted to say that the base of the larger triangle is 12, but 12 is not the entire base of the larger triangle. The base of the larger triangle is the entire shape. Remember, the large triangle is the whole thing. So the base is the distance from Matt to the net plus the distance from the net to where the ball is going to land. So it's that entire distance there is the base of the large triangle. And because these two triangles are similar, these ratios should be equal. They should be in proportion. Okay, so I'm going to go ahead and combine my like terms here. 12 plus 6, of course, is 18. So when it's all said and done, we will have 0.9 over 6 is equal to x over 18. Okay, so how do I solve this? This way we solve any proportion, the easiest way, is to cross multiply and divide. So we're going to do 6 multiplied by x. Let's pick a color it's a little easier to see. Let's do 6 times x in red. 6 times x is going to give us 6x. And then going the other direction, let's go ahead and stay blue here. We'll do 0.9 times 18 in blue. You could do 0.9 times 18 on a calculator if you like. Um, I don't have a calculator handy, so I'm just going to leave it as 0.9 times 18 for now. My goal here is to get the x by itself. So that means we need to next use the division property of equality and divide by 6. So let's go ahead and do that. Divided by 6, divided by 6. And so this is the division property of equality. Now 6x divided by 6 is just x. With a calculator, we could do 0.9 times 18 divided by 6, and I believe the answer you're going to get is 2.7. And the reason I think that's the answer is because if you don't have a calculator, you can do a neat little trick here, which is that you can do 18 divided by 6, which is easy to do without a calculator. 18 divided by 6 is 3. And then we can do 0.9 times 3. So 9 times 3 is 27. So 0.9 times 3 would be 2.7. So I'm pretty sure with a calculator you will get 2.7 because that's what I get without a calculator, 2.7. Now we don't want to just stop at 2.7. The question said, at what height should Matt hit the tennis ball? Let's do better than just 2.7. Let's say Matt should hit the ball from a height of 2.7 meters. 2.7 is the numerical answer, but let's do better than that. Let's do better than just the number. Let's go ahead and say what the number means. So we answered the question. We answered the question in context. What does the answer mean? And the way that we did it was by drawing this diagram, we were able to see, oh, this is two similar triangles. How did we know the triangles were similar? Because of the angle-angle similarity postulate. We had two congruent angles in each triangle. One of them was a right angle, and one of them was this really cool angle right here that they shared. So we knew they were similar triangles. And if they are similar triangles, that means their sides are proportional. So we were able to set up this proportion using the side lengths of the triangle. And once we had that proportion set up, it was a simple matter of doing cross multiplication and division to figure out what our missing side was.